we have been talking about the conservation of momentum. So I'd like to draw out one more consequence of this law of conservation of momentum. And this is, we're talking about corollary 4 in Newton's Principia in book 1. And specifically, I want to talk about when he's lemma 23. So this is kind of a subpoint in corollary 4. And here Newton mentions that if no external forces act on a system, then its center of gravity retains its state of motion. Its center of gravity retains its state of motion or rest. Okay, so let me draw a picture to try to explain what he's talking about here. I'm going to use some tools I haven't used before. So let me go like this. I'm going to draw the trajectory of two objects. So imagine we have one object that's moving along this trajectory right there. Okay, and let's suppose we have another object that is moving along, oh, I don't know, let's even make them crossing, like this trajectory right there. Okay, and let me draw these two objects. So let's suppose that this object right here okay, so I'm drawing the position of a mass at subsequent moments in time as it's moving along this trajectory. Okay, and now let's suppose that there's another object that's a bit bigger object that is moving along this trajectory. It's moving a little bit faster, so I'm going to draw these a bit farther apart. I think I have 5 on each of them, right? Okay, so this is at time 1. This is at time 2. That's there and that's there. At time 3, he's there and he's there. At time 4, he is there and he is there. And at time 5, he is there and he is there. Okay, and now what I'm going to do is I'm going to, let's use the same color. And I'm going to connect these so these two, the center of gravity is going to lie somewhere along that line. And at this moment in time, the center of gravity is going to lie somewhere along this line. And at this moment in time, the center of gravity is going to lie somewhere along this line. And at this moment in time, the center of gravity is going to lie somewhere along this line. And at this moment in time, the center of gravity is going to lie somewhere along this line. Okay? And here's the point, is that at this moment in time, the center of gravity is going to lie a little bit closer to the heavy ball than to the light ball. So let's draw the center of gravity position to be right there. This ratio of that distance to that distance remains the same. So what's going to end up happening is we are going to have the trajectory of the center of gravity is going to travel in a straight line. So if the center of gravity was here at the first moment in time, the center of gravity is going to be here at the next moment in time, here at the next moment in time, here at the next moment in time, here at the next moment in time. So it is always going to be going in a straight line. So this ball is going in a straight line, this one is going in a straight line, and the center of gravity is also going in a straight line. And it doesn't matter whether these two balls ever collide or cross or do some other funny thing, as long as all they're doing is exerting forces on each other, the center of gravity trajectory retains its state of motion. And moreover, this applies not merely to two objects, but to any number of objects. How do we know that? Well, we could take 3 or 4 or 5 or 100 objects. We could find the center of gravity motion of the first two, and that would be describing the motion of that two-body system. Then we could add in a third object and find the center of gravity between that new object and the previous center of gravity motion. And of course, that would be going in a straight line. And that would be the center of gravity motion of the three-body system. And then add in a fourth and a fifth and so on. And you will always find that the center of gravity of 2, 3, 4, 5, 100, 1,000, or n objects always moves in a straight line at a constant speed, provided there are no external forces acting on this system of bodies. Okay. Now, I probably have time to just say, go on to corollary 6 and 7, to say something quickly about each one. So, I'm sorry, corollary 5. What does corollary 5 say? Corollary 5 says that corollary 4 holds whether the space is at rest or moving at a uniform speed. So corollary 4 holds, or this one up here is true, whether the space in which these 2 things or 3 things or 10 things are moving is at rest or moving at a uniform speed in a straight line. Okay, so in other words, let's talk about this. Maybe use a different example. Let's suppose we have an air hockey table that we're looking at from the top, and we've got all kinds of maybe air hockey pucks bouncing around on this, but their motion is such that when you consider all the balls moving, all the air hockey pucks moving, the center of gravity, let's suppose, is moving in a straight line. So this is the velocity of the center of gravity. It's moving in a straight line. Okay, I guess I should be careful. They can't really be bouncing off the walls because then there'd be forces from the walls acting on them, as long as they're not bouncing off the walls. So if you've got these pucks moving around here, the center of gravity motion is in the same direction. Now, let's suppose that this entire air hockey table is moving in this direction at a constant speed. Well, what's going to happen is we can simply, what this corollary says is we can just take the velocity of the center of gravity, add to it the velocity of the space or the relative space in which they're moving, and you can add those two together and you'll find that this new center of gravity motions, v center of gravity prime, is still going to be a straight line. It's just the sum of the center of gravity motion within this space and the speed of the space in which it's moving. That's what corollary 5 is stating. Okay, and let me just say something about his corollary 6. Corollary 6 says that bodies retain their same motion relative to one another even if the center of gravity feels an impressed force. Okay, so for example, due to gravity, let's say. So let's imagine we've got a crane. This is a very tall crane, and this crane has a string with a bomb attached to it. So this is a bomb attached to it. Okay, and the bomb, when you release it, it starts going down, and the center of gravity falls. And as you know, as it's falling, it speeds up. So at each moment in time, the center of gravity moves a little bit bigger distance, right? Because its speed is getting greater and greater. So its center of gravity is accelerating. The bomb is accelerating downward. Its center of gravity is accelerating downward. And let's suppose that after a moment, it explodes and breaks into 2 pieces. Okay, so when it gets right here, it breaks into 2 pieces, and these 2 pieces go flying apart. Okay, so what's going to happen as they fly apart? The center of gravity is still going to do the same thing. The center of gravity is still going to be falling at a constant rate due to gravity. This is sort of an external force acting on this. But they're going to be moving away from each other in a way so that if you were just watching the bomb fall and moving downward at the same speed as the bomb was falling, they would be moving away from each other at the same speed as if you were just watching it sitting still. So in other words, if I were to take a camera and move the camera down, drop the camera with it, those two would be moving relative to one another in the same way as if the entire system was not falling. That's what he's claiming in corollary 6. This is going to be relevant when he comes back to talk about things like when you have the moon and the earth orbiting around each other. around their common center of gravity. So if you have the common center of gravity of the moon and the Earth, they're orbiting each other. It doesn't matter that the sun is going to be pulling on both of them and they're both going around this orbit. Their motion relative to one another is going to be the same as if they were just sitting still. Okay, we'll stop there. And next time that I lecture, I'm going to do a lot of example problems.